Okay, so the following problem that we're going to attempt next states the following. The red spectral line of lithium occurs at 671 nanometers. Calculate the energy of one photon of this light. So the first thing that we want to note is that the energy of a photon is related to the corresponding frequency. And we learned this equation in class, which is energy is equal to Planck's constant times frequency. Perfect. So once we take note of the equations that we're going to be utilizing, the following problem is going to become a lot easier to tackle. So they give us a wavelength. Okay, they give us a spectral line of lithium. How do I know this is a wavelength? Well, I look at the units. The units are in nanometers. Okay, that corresponds to that of wavelengths. Okay, frequencies are always in units of 1 per second. And they're also telling us this is the spectral line. As we've learned that earlier in the semester, the different spectral lines that you can have, or the different emission spectrums you can have for specific types of elements, etc. So once we note that we have wavelength, so they give us wavelength is equal to 671 nanometers. Okay, well, we look at this and we can't exactly plug in wavelength immediately into the following problem. What we'll have to do is determine the frequency, which we know the speed of light is equal to wavelength times frequency. So we can solve for frequency. Once we solve for frequency, we can then plug in our frequency into the very first equation that we noted up above, what that energy is equal to. And then once we do that, we can then solve the problem in the following fashion. So let's first start off with solving for frequency. We know frequency is equal to speed of light divided by wavelength. We know the speed of light is equal to 3.00 times 10 to the 8th meters per second divided by the wavelength. Well, the first thing that we have to remember is we have to make sure our units match. So we have to convert this into meters. So 671 times 10 to the negative 9th meters. So perfect. Once we do that, we can plug it in. 671 times 10 to the negative 9th meters. My meters and meters cancel out. Let me get a new pen. And this will be equal to 4.47 times 10 to the 14th per second. Okay, perfect. Now that we have frequency, we can then plug this back into the equation up above and solve for energy, because we are calculating the energy of one photon of this light. So we have energy is equal to Planck's constant, and we know Planck's constant is 6.63 times 10 to the minus 34th joules times seconds. We multiply this by our frequency, 4.47 times 10 to the 14th per second. Seconds and seconds cancel out, and this will be equal to 2.96 times 10 to the negative 19th joules. So it's important to make sure that when you come to your finite answer, you want to double check a handful of things. Do you have the correct units for whatever you are calculating? We know energy will have units of joules, so perfect, we have the correct joules. We then can plug this answer back in, and we can solve, and we can double check this by either solving for frequency and make sure that we get that same value, or solving for the Planck's constant and make sure you get that same value out. That's just like one small way to kind of check to make sure at least you're inputting the values correctly into your calculator.